Alright, so last time we defined the natural numbers by introducing some intuitive axioms that kind of capture the properties that we expect them to have. And just to reiterate, I've rewritten them down here. The first one being that we've decided there's a special element in the natural numbers which we're going to label with the symbol and name 0. And this really becomes more relevant as we bring in axioms 2 and 3, but the point of this one is basically to say that in our system of counting, counting starts at 0. Axiom number 2 then introduces sigma, which is basically meant to be interpreted as the counting function, in that it's a function that takes a natural number as input, gives a natural number as output, and what is it doing to the input when it transforms it? It's just telling us, well, what is the next higher number higher than the input? It counts up by 1. Well, what properties should a function that counts up by 1 have? Well, first of all, it should be an injective function, and property A of sigma is really just the definition of an injection. It tells us that given if we feed two possibly different inputs into sigma and we get the same output, that tells us that our inputs really were the same to begin with. To put that differently, we can also say that two different numbers will never count up to the same number. Property B of sigma is telling us that you'll never see 0 as the output of sigma for any natural number that you give it as input. In other words, nothing counts up to 0. Our set of natural numbers is really just the set of non-negative integers. But of course, that's going to be a property that we give to it, though to mention it now is to say that this is kind of a property that we hope to endow it with by giving it these axioms. Number 3 is the most long-winded one of them all, and likewise it has a long-winded kind of English explanation, but what it's really saying is that the set of natural numbers is exactly the numbers that you can reach by starting from 0, which is why we have this guarantee that 0 is in this subset of the naturals, and successively counting up by 1. So if I know that some given number is in S, I am then guaranteed that sigma of n, in other words, the number I get when I count up by 1, that number is also in S. If these two guarantees are both true, this is kind of a single guarantee because it's the implication itself which we want to be true. When these two together are true, then what that tells us is our subset of the natural numbers S, well, it's not really just a subset, it's actually the whole thing, right? So to kind of put this in perspective, this means suppose we are told initially that 0 is in S. Well, together with the second guarantee, this implies that 1 is in S. But knowing that 1 is in S implies that 2 is in S, and so on and so forth. And so what is S but the set of numbers that if I just start at 0 and continue to count up, it's the set of all the numbers I can eventually reach. And we want the natural numbers to be exactly that set. It's just the set of all the counting numbers, all the numbers that you could eventually count up to. So now that we've defined the counting numbers, let's use them to do exactly that, which is count. And what are we going to count? We're going to count the number of times that we have used a function. So what I mean by that is, say we're given some function f which takes inputs from some given set and gives outputs in the same set. We're going to define what it means to apply f n times to an element of S. So here we have that n is some natural number and that x is some element of our set S. And what does it mean for us to apply f n times to x? Well, first, we're basically going to give a recursive definition. So first, we're going to define f applied 0 times to x is just a function that goes from S to S and it sends x to itself. So f is basically, it's the identity function. It means it's the function that takes the input, doesn't do anything to it, and then just gives that input right back to you. And now here comes the recursive definition of x. What does it mean to apply f to a general number? Well, I'm actually going to tell you what it means to apply f to a number one more time than that number. So I'm going to tell you what it means to apply f sigma n times to x. That, by definition, we'll put the colon in front of the equal sign to signify that this is a definition. By definition is going to mean that we apply f to the result of having applied fn to x, or fn times. Now, how does this make sense? Well, so we know what f0 does, right? And 1, more or less by definition, is going to be sigma of 0. It's the number that's 1 higher than 0. So what does it mean to apply f1, f once to x? And you'll see how this fits in with our kind of intuitive idea. Well, going by our definition, since 1 is the number that you get by counting up from 0, this is effectively asking us to apply f sigma 0 times to x. But that means applying f to the result by this definition here. It means applying f to the result of applying f0 times to x. But by our first definition, I'm going to use this arrow to bring our cursor up here. By our first definition, this ends up just being x itself. F applied 0 times to x just gives you x back. And this is just f applied to x then. So applying f once to x is just asking you to apply f to x. And this seems kind of trivially obvious if you already know what the natural numbers are. But remember that we're defining the natural numbers from the ground up. So they don't yet have any of the properties that we intuitively expect them to have. And what the purpose of these 3 axioms that we've laid out here, the piano axioms, the purpose of these is to be a set of base, like the most fundamental basic properties that the natural numbers have, from which we are going to derive all the other properties. And to illustrate this further, let us show that our definition of applying functions multiple times respects this law. We want to show that for all n in the natural numbers, given some function that goes from some set to itself, we want to show that this property is true. Say I apply f to the result of having applied f n times to x, where x is some element of s. We're going to show that this is the same as applying f n times to the result of f of x. Now again, this is something that we would intuitively expect to be true, but we're trying to build math from the ground up. So everything that we want to be true, aside from axioms, is something that we have to prove using the axioms and other things that we've proven before. And of course, since we laid out the axiom of induction, we're actually going to use induction to prove this. So we're going to induce on n. So first, we're going to assume in our base case that n is 0. We're going to show that 0 is a member of the set of numbers that satisfy this law. Okay. How are we going to do that? Well, we're going to show, what we really need to show then is that f of f applied 0 times to x. Well, what does that equal? From our definition, f applied 0 times to x just gives us x. So this is really the result of f of x. But f of x is trivially, obviously, equal to itself. But that means it's the result of having done nothing to itself, which means it's the same as this. And that's exactly what we need to prove to assert that the base case is true. We've now shown that this law, we have yet to show that it's true in general, but it's definitely true when n equals f. And we've done that with a series of transformations that have been based on nothing but our axioms and things which we have previously defined. Now we move on to the inductive step. So we're going to say, suppose we know that this law is true let's just finish writing it out here. Suppose we know that this law is true for some fixed n. It's not true for every natural number. That's not what we're assuming. Let's just say maybe someone told us, or maybe we proved that it's true for some specific value of n, like maybe it's 0. But we're not going to ascribe that yet. Knowing only that it's true for some n, we need to prove, rather, that this is true for sigma of n as well. Sigma of n as well. So what do we really need to show? We need to show that f applied to the result of f applied sigma n times to x is equal to f applied sigma n times to the result of f of x. Okay, so what we're going to do is we're going to tackle both sides of this equality separately and show that they're equal to each other at the end. And because we don't yet know that they're equal, we're not going to write an equal sign just yet. So let's look at what the red side is going to give us. The red side being this one. Well, this, by definition, is going to be equal to f applied to. Inside here, we're going to break down this term, f applied sigma n times. From our definition, this is going to be f applied to the result of applying f n times to x. Defining things recursively always forces us to say things in a very verbose kind of way. Okay, so what does this tell us? This tells us that we have f applied. Actually, we're just going to leave this like this. Now let's look at this side, and we're going to color it blue to highlight that it's different. So we're going to kind of remove as many sigmas as we can here. We're going to expand this f applied sigma n times into f applied to f n, which itself is being applied to f of x. Okay, but look at this term here. This, according to our inductive hypothesis, right, is equal to that. So we're going to swap around the terms, and we see that what we have is the same expression, right? With nothing but a series of valid transformations, we've transformed both of these different looking statements into the same expression. And since these two are equal to each other, we've now completed our proof of the inductive step. And that shows via induction, let's use a black check mark to indicate that we've proven everything. We've now proven via induction that this law in general holds for all n. Now why? Because if we let S, which is a subset of n, be the subset for which the law holds. Now, what have we demonstrated? Because of our base case, we proved with our base case that 0 is an element of S. What have we proven with our inductive case? Well, we've proven that if I know n is in S, I can demonstrate for you that sigma of n is also in S. But by induction, axiom number 3, we know that this implies this subset of the natural numbers is really all of the natural numbers, which ultimately tells us that this law works for all n in the naturals. And this is going to be a recurring strategy that we're going to use to prove some other things. Now, today we've counted repeated applications of some arbitrary function defined on an arbitrary set. But the one function which we've really kind of inspected and that we might really be interested in is this sigma, our counting function. What might it look like if we start to apply sigma multiple times to some given number n? And for that, you'll have to tune in next time.